In this video, we are going to go over some naming conventions and some important properties of aromatic compounds. For a lot of these aromatic compounds, they just use the common names for them. In fact, I don't think I've ever seen any of these things called by these systematic names here. They're always called by these common names. So if we have an alcohol coming off of our aromatic ring, then it's a phenol. If it's just a methyl group, it's toluene. If it's an amine group, it's aniline. If it's this methoxy group, then it's anisole. Similarly, if we have this vinyl group, then it's styrene. If we have this acetyl group, then it's acetophenone, and then this one is benzaldehyde and benzoic acid. So these are some very common benzene derivatives that show up quite often in an organic chemistry lab. And with a lot of these other derivatives, they're usually just named by the substituent onto the benzene. So for instance, if we have a tert-butyl group on it, then it's tert-butylbenzene. If there's a nitro group on it, then it's nitrobenzene, and so on and so forth. When we start having more than one substituent on it, then we have to have a few other naming conventions. One of the ones that you will run into with these aromatic compounds is this ortho, meta, and para naming convention. So if we have two substituents and they're just one carbon away from each other, they call that ortho, or they put the little italic O on it like that to mean ortho. If they are one further away from each other like this, then they're called meta, or they'll have the italic M on it. And if we have them exactly opposite each other like on here, then they call it para, or they'll put the italic P there. And this convention will get used interchangeably, whether it's the 1,2 or ortho, or the 1,3 or meta, or the 1,4 or para, like that. So using the ortho or the 1,2, the meta or the 3, the para or the 4. So again, you want to make sure that you are looking out for either of those two because they can get used interchangeably. If we don't know or we don't care where these substituents are relative to each other, you will often see it written like this, where it's sort of shown with a line in between two bonds there, telling us that we don't know where that substituent is and or we don't care where it is. If we have 3 or more of these substituents, then we want to start numbering from one of these substituents. Usually it will be whatever is considered the backbone. So for instance, this one right here is a phenol backbone, so it has that alcohol group there. And so we start with the 1 carbon where the alcohol is attached, and then we just number to the nitro group. So if that's 1, this would be 2, that would be 3, and that would be 4. And so we see this is 2,4-dinitrophenol. If we have all the same groups, then what we want to do is we can just essentially, like on this one, just start numbering from wherever we want on any of these groups because they are all the same. If they are not equally spaced out from each other, then we would want to start such that we have the lowest numbers possible and we get to the next substituent fast. So if, say, this nitro group wasn't here, but was instead right here, then we would want to start numbering, say, from right here, 1, 2, 3, and 4, and so that would get us to those substituents the fastest, and it would reduce the numbers on them as much as possible. Other of these polysubstituted benzenes end up just using the common name quite often. Even though there is no systematization of these names, they are just used for the common names, which is quite common with these benzene derivatives. When the aromatic ring is itself considered a substituent, then we call it the phenyl group. So that's with a YL at the end, so don't confuse that with the phenol. So when I teach this, I oftentimes try to really overpronounce that name. So I'll say phenol and phenyl, trying to make sure that I'm distinguishing between those two things as much as possible. And these can often be represented with a pH. The book here says they can be used with the phi symbol like that, but I don't think I've ever seen anybody use the phi symbol. It's pretty much just always the pH. And so the pH just represents the aromatic ring, the phenyl group. Similarly, we can have the benzyl group, so this has the YL at the end, and that's if we have this extra carbon as part of it right here. So these would be the benzyl groups right there. So it contains both the aromatic ring and that methylene group as part of it. These substituents can then also have their own substituents, and so we oftentimes call those aryl groups. So ARYL, like that. So that would look something like this, where we have not just the aromatic ring, but also substituents coming off of the aromatic ring. And if we look at a few of the physical physical properties of these aromatic compounds, we see we can have the melting point, boiling point, and density. These are going to be all over the place depending on what it is. Three of the ones that I wanted to look at are these ones down here, so the O, M, and P dichlorobenzene, and we can see these structures of those right here. And so we see even though these have the same molecular formula, they can have different boiling points and melting points depending on where these substituents are relative to each other. And that's because, as we can see over here, we can get these different dipole moments on these molecules depending on where these substituents are relative to each other. It's also going to depend on what these substituents are. So this trend here would not necessarily hold true for all ortho, meta, and para substitutions, because if we have something other than chlorine, or maybe if they are actually two different things, then they can have different properties. But what I wanted to show here is just that having them in the different positions is important for the physical, and as we'll see in later videos, the chemical properties of these compounds. And finally, a few important things to think about when we are in the lab. So the IR, the infrared spectroscopy of the aromatic ring. The aromatic compounds are readily identified by having a stretch around 1600 wave numbers. And the CC bond is lower in frequency than the isolated alkenes, which show up between 1640 and 1680 wave numbers, and just the simple conjugated dienes, which is between 1620 and 1640. And this is because the bond order is 1.5 rather than 2. So we can look at these two examples here. We have this toluene right here, and then we have this 3-methyl 1-cyclohexene right here. And we see with the toluene, which has the aromatic ring, we have this peak right here, which is right around at that 1600. It might be hard for you to see, but right there is the 1500. This would be the 1600 right there, and so we end up getting that band right there at about 1600. Then with the HNMR, what we see is because we have this induced magnetic field, because of the way that the pi bond system forms this continuous loop, we can actually get a current moving through that's induced by the magnetic field. When we have a moving current, we then induce a magnetic field, and so that can actually make the hydrogens on our benzene ring, which are shown right here and here, look like they are de-shielded, because we have that extra induced magnetic field that would be pointing in this direction out by the hydrogens. And so what that does is it causes the peak on our NMR to get moved quite a bit to the left over here. And so it will usually show up somewhere between 7 and 8. I talk a bit more in my organic chemistry lab videos about this, and I go into more about the splitting that can happen, but for this video the purpose is just to say that we get a lot of de-shielding going on with these hydrogens. So even hydrogens on an alkene, just a single double bond, would show up probably somewhere more in this region right here. So having that aromaticity can actually cause a quite large of a shift in where that peak shows up. Then finally, in the mass spectroscopy, the one thing that we want to point out is that we can end up making this tropylium ion right here. And so what we see is we're going to get this split right here. And so we're going to end up with a positive charge on this carbon. We can then get an alkyl shift. So this will move out over that carbon, and we end up with the 7-membered ring right there. And that is pretty stable because it is itself aromatic, and so it has that aromatic stability. And so we see these peaks showing up at 91 m/Z in our mass spectroscopy when we have aromatic rings. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.